All right, so today is going to be the first of 3 lectures regarding power in AC circuits. This is the one that's probably the most math heavy, so I'm just giving you guys a fair warning. So let's say that I have a linear network. This lecture is going to be on instantaneous and average power, by the way. So I was saying a moment ago, let's say that I have a generic network like so. So this is just a linear network containing some combination of resistors, capacitors, inductors, possibly independent and dependent sources. Okay. And this is a 2-terminal network. And this network is sinusoidally excited such that there is a sinusoidal voltage drop across the terminals of the network V of t and a sinusoidal current flowing through the network I of t, where, to be very explicit, V of t will be of the form Vm cosine omega t plus theta v, and I of t will be equal to Im cosine omega t plus some phase angle theta I. Okay. The instantaneous power that is absorbed by the network, so that's power as a function of time. And by the way, this is the same thing as the instantaneous power supplied by our source, is simply going to be the product of our voltage waveform V of t and our current waveform I of t. So when we multiply those two functions together, we're going to wind up multiplying those cosine functions. And so I'm going to hit you guys with yet another trig identity. I know you're so excited. That'll help us figure out how that's going to work. Okay. So the trig identity that I'm going to use, I'm going to put over here in blue. And that is that the cosine of some angle 1 times the cosine of some angle 2 is equal to 1/2 the cosine of angle 1 minus angle 2 plus 1/2 the cosine of angle 1 plus angle 2. In our case, angle 1 is omega t plus theta v, and angle 2 is omega t plus theta I. So when we apply that trig identity, what we're going to wind up getting is 1/2 the magnitude of our voltage times the magnitude of our current times the cosine of, and so now let's subtract angle 2 from angle 1. So the omega t's are going to cancel each other out, and we're going to be left with just a theta v minus theta I. And then now we have the second half of our trig identity. 1/2 Vm Im cosine. Now we're going to add those together. So omega plus omega t is going to look like twice omega t plus theta v plus theta I. This long thing here is our generic relationship for instantaneous power. Okay. So this equation works for literally anything. can work for a network, can work for an individual component. Doesn't matter if it's a resistor, capacitor, inductor, combination thereof, works for voltage sources, current sources, dependent sources, the whole thing. This is our generic relationship that literally works for everything. And in order for us to apply this equation, we need to know both the phasor voltage drop across our network of interest and the phasor current flowing through our network of interest, right? So even though we have a time domain relationship here, because it's a function of time, we're still going to use our frequency domain circuit analysis in order to figure out the pieces that go into this equation, okay? So Vm is just the magnitude of a phasor voltage. Theta V is just the phase angle of a phasor voltage. Im is just the magnitude of a phasor current. Theta I is just the phase angle of a phasor current. So we're not going to ever have to do time domain circuit analysis, even though this equation suggests that everything is going on in the time domain. All right, so what I want to do now is I want to make kind of a generic plot for this. So I want to illustrate a couple of things. So our vertical axis is going to be our power as a function of time. And our horizontal axis will be time. So this first term, 1/2 Vm Im cosine theta V minus theta I, all of those quantities are constants. And the cosine of a constant is a constant itself, which means this first part just represents a DC term, our instantaneous power relationship, right? So I'm just going to put a little thing under here. This bit is DC, and then this guy right here is obviously AC. What's interesting about it is that it's actually at twice the frequency of the voltage or the current. So the power oscillates twice as quickly as the voltage signal or the current signal in an AC circuit, okay? So if I were to make a plot of our instantaneous power, it might look something like this. So this dashed line that I'm putting right here represents that DC component. And then superimposed on top of that DC component, I'm going to have that sinusoidal signal. Okay. So starting with just a generic overall phase angle of 0, because it's easier for me to draw, it might look something like this. So for this particular representation, we can glean a couple of interesting things, okay? So if we look at this as a function of the absorbed power of the network, anytime P of t is positive, that means that our network is absorbing power. And anytime that our power is negative, that means our network is actually supplying power back to the source. So we have some specific instances here and here where our network is actually acting as the source and is sending power back to the excitation source in the system. We are always going to see something like this occur whenever there are any energy storage elements in our network, meaning anytime that we have a capacitor or anytime that we have an inductor, we are going to wind up sending power back to the excitation source. We're going to talk about that phenomenon in a lot more detail when we get back from the Mardi Gras break, when we're talking about complex power and particularly power factor correction. But effectively, we can observe right here that there's some portion of the power that's being returned to the source that generated it. Okay, so that's a very interesting thing. Let's take another look at this DC component here. Okay, so we can see graphically here that exactly half of the time our instantaneous power signal is above this dashed line, and exactly half of the time it's below this dashed line. So what does that dashed line then represent? The average, exactly right. So it turns out that the DC component of our power is literally just the average power absorbed by our network. We will mathematically prove that in a couple of minutes, but literally just by looking at the graph and understanding what's going on, we can see that that has to be true, right? So the average power is actually a quantity that's already built into our instantaneous power relationship. Yes, sir. So if we look at this amplitude here, think I'm understanding your question, right? So we have this distance, which is about 2.5 units from the peak value to the average, and I should have this distance, which is also about 2.5 units from the bottommost peak and the average. So it's still perfectly okay that we are having some amount of supplied power. In fact, what we're going to wind up seeing here in a couple of minutes is for a capacitor or an inductor by itself, the average value is always just going to be 0. And for a resistor, because it's literally incapable of supplying power, the average value will always be exactly between the peak value and the horizontal axis. Okay. All right, so speaking of our behaviors in resistors, capacitors, and inductors, let's go ahead and sort that stuff out. We're going to bring back some of the relationships that we came up with in our phasor relationships for resistors, capacitors, and inductors here. So if I were to have a resistor, so for a resistor R, we know that the magnitude of the voltage drop is simply equal to the magnitude of the current times the resistor value. And we also know that the phase angle of the voltage and the phase angle of the current are the same thing, right? So what I'm going to do is I'm going to use these relationships to come up with a way to express the instantaneous power absorbed by a resistor only in terms of the voltage or only in terms of the current, so that we don't have to know so much information in order to figure out what's going on, okay? So in terms of the voltage, we're going to have P of T 1/2. Well, the magnitude of the voltage is already in terms of voltage. The magnitude of the current could be written as Vm divided by R. So I would have Vm times Vm divided by R, which is actually going to look, let me move this up, look like Vm squared over R. Then we're going to have cosine of theta V minus theta I, right? I'm literally just going through our generic equation, but putting everything in terms of our voltage. So what's theta V minus theta I for a resistor? 0. So what's the cosine of 0? 1. Okay. So I'm going to put in brackets here, 1 plus, and now since we have another 1/2 VM IM term. Now we're going to talk about that bit. So we're going to have cosine twice omega t. And then since theta v and theta I are equal, theta v plus theta I could just be written as twice theta v. So that's our relationship for the instantaneous power absorbed by a resistor in terms of only the voltage. Now, based on our knowledge that the DC portion of the instantaneous power is simply the average power, what would the average power of a resistor be expressed only in terms of the voltage? So effectively, we're throwing the time varying part away. Okay. So the cosine omega t plus twice theta v bit gets thrown away. That's the AC part. Whatever's left is the average power, which would just be the 1/2 VM squared over R. Does this relationship look kind of familiar? So in a DC circuit, the average power absorbed by a resistor in terms of only the voltage was just V squared over R. So in an AC circuit, we just cut it in half, and it's because we're multiplying those two sinusoidal functions together. And we can see from that trig identity that there's a distributed factor of 1/2. So that's where that 1/2 is coming from. We can do something similar to put everything in terms of just the current, right? So the 1/2 is just going to look like 1/2. VM could be expressed as IM times R. We multiply that by IM, giving us IM squared times R. Cosine of 0 is still 1. And now we can say that theta v plus theta I is going to look like twice theta I, since our angles are the same. And expressed only in terms of our current, our average power is given by 1/2 IM squared times R. So before we move on to inductors, anybody have any questions about where these relationships came from? Hopefully pretty straightforward. All right. So for an inductor L, what's our relationship between the magnitude of the voltage drop across an inductor and the magnitude of the current flowing in the inductor? So we know that phasor voltage V should be equal to J omega L times phasor current I. And then we just take the magnitude of both sides, right? So the magnitude of phasor voltage V is Vm. The magnitude of J omega L is omega L. The magnitude of phasor current I is just Im. What's our phase angle relationship? You guys literally just did a lab on this Wednesday. What was the difference in the phase angle for your inductor? Should come out to be positive 90 degrees between the voltage and the current, right? So theta V should be equal to theta I plus 90 degrees. We discussed this previously, but in an inductor, the voltage always leads the current by 90 degrees, or transversely, the current lags the voltage by 90 degrees. That's what we have written right there. So let's look at our instantaneous power relationship in terms of the voltage again. So the 1/2 is going to look like 1/2. The VM is going to look like VM. IM can be expressed as VM divided by omega L. So we're going to have VM squared over omega L. And now we come to the cosine bit, okay? So let's scroll up here just a smidge so we can talk our way through this, right? So we're going to be subtracting theta I from theta V, okay? So I can see from this relationship, let me just put a quick aside kind of thing here, that theta I is just theta V minus 90 degrees. All I did was move the 90 degrees across the equal sign, right? So when I have theta V minus theta I, that's now going to look like theta V minus theta V plus 90 degrees. The theta V's cancel each other out. And now I'm just taking the cosine of positive 90 degrees, which is 0. So there is no DC component to the instantaneous power absorbed by an inductor. So moving on to the AC part, we're going to have cosine twice omega t. And so now I'm going to add theta V and theta I. So that's going to look like twice theta V minus 90 degrees. And here we can put that our average power is simply 0. Following suit for the instantaneous power absorbed by an inductor, expressed only in terms of current, this is going to look like 1/2 Im squared times omega L cosine twice omega t plus twice theta I plus 90 degrees. Anybody have any questions, comments, or concerns about our inductor relationships? All right. And so now let's move on to capacitors. So in a capacitor, the magnitude of our current is equal to omega C, times the magnitude of our voltage. And we know that theta I is equal to theta V plus 90 degrees, right? So doing the same thing I did a moment ago, I could then say that theta V is just theta I minus 90. So in terms of our voltage, this is going to look like 1/2 Vm squared times omega C. Now I'm doing the cosine bit. So I'm going to have theta V minus theta I. So that's going to look like theta V minus theta V minus 90 degrees. What's the cosine of negative 90? Also 0. So a capacitor doesn't have any average power absorbed either. Moving on to the AC portion, we're going to have cosine twice omega t plus twice theta v plus 90 degrees. And expressed in terms of current, we're going to have 1/2 Im squared over omega c cosine twice omega t plus twice theta I minus 90 degrees. And I'll just write this down here as P average is equal to 0. So here are all of our instantaneous power relationships. I just want to kind of recap things here really quickly. Okay. So at the very top, we have this expression that I boxed in red. And this is our generic expression that can be used for literally anything. Okay. Then we took the time to develop equations for just resistors. So anytime we have just a resistor, we can use either of the two equations for resistors, depending on whether we know the voltage across the resistor or the current flowing through the resistor. Patrick, how may I help you?
When you say just resistor, you mean like only resistors in the circuit, or like finding power at the resistor?
So finding power at the resistor would require us to know just the voltage drop across the resistor or just the current flowing through the resistor. Yeah, so it's not for a network containing only resistors, but if we're only interested in the power being absorbed by just a resistor by itself, we can apply these equations. We'll see this in a minute when we do an example problem, okay? Same thing for our inductor relation. Yes? So omega L is the magnitude of the impedance. Omega C is the inverse of the magnitude of a capacitor, right? So if we had a frequency domain circuit and we were interested in finding the instantaneous power absorbed by an inductor, if we know the impedance of the inductor is J2 ohms, then we know that omega L is just 2 ohms. So we actually do have everything we need, even though we never explicitly learned what the value of the inductance was in particular. Same thing for capacitors, right? We just throw the J bit away and we're left with a magnitude of 1 over omega C. 1 over omega C is why we have the omega C in the numerator effectively for the voltage relationship. All of these relationships are effectively 1/2 voltage or current squared, and then we are multiplying the current by the magnitude of the impedance or dividing the voltage squared by the magnitude of the impedance. Good question. All right, so our inductor and capacitor relationships are effectively the same situation. We have a relationship only dealing with the voltage drop across the element or only dealing with the current flowing through the element so that we don't need both pieces of information. So let's take a look at our in-class assignment for today, which, by the way, happens to be the problem that we're going to look at is also one of your web work problems, done very intentionally. So we are told that there are 3 circuit elements that are connected in parallel: a current source, a resistor, and a 15 millihenry inductor. So in the time domain, we're going to have something like this, where here's Is of t. Here's our resistor R. And here is our inductance L. And what we're interested in determining is the instantaneous power absorbed, I want to make that very clear, absorbed by each of the elements at some specific time, okay? So if I were going to try to solve for the instantaneous power for my current source, what pieces of information, excuse me, would I need? This isn't supposed to be a trick question, by the way. Voltage drop across the current source and the current flowing through the current source, right? Just normal power stuff, okay? If I were trying to find the instantaneous power absorbed by the resistor, I would need either the voltage drop across the resistor or the current flowing through the resistor, or both. For the inductor, I would need the voltage drop, the current, or both. So I would argue that if we're able to determine this voltage V of t, we will have enough information to perform all of the calculations for this problem, right? So this is probably the quote unquote smartest way to do it. So the first thing that we would do is we would convert this circuit from the time domain into the frequency domain, because I cannot emphasize enough how we will never do analysis in the time domain again. So what is the phasor representation of my current source going to look like? So 100 angle 0 milliamps, which I'm going to choose to express as 0.1 angle 0 amps, so that I'm just working in base units. Okay. What is the impedance of my resistor going to be? 1 kilo ohm, because the resistor doesn't change, right? What is the impedance of my inductor going to look like? So it's always going to be positive, so I'm just going to go ahead and throw my J out there. Now I just need to figure out omega and L. Well, L was given to me as 15 millihenries. What's omega? 2 times 10 to the 5. So somebody get your calculator out and multiply those two things together. All right, so J 3 kilo ohms. Absolutely correct. And now we're trying to solve for this phasor voltage V. Okay. So how can we solve for this phasor voltage V? Technically, yes, but that's more work than I'm willing to do. You're overlooking something obvious. Yeah, so just use Ohm's law. I times ZEQ. So that's going to look like 0.1 angle 0 degrees amps times 1 kilo ohm times J 3 kilo ohms divided by 1 plus J 3 kilo ohms. So let's throw that in our calculator. This calculator is set up to give me rectangular, so I'm going to have to fix that in a moment. So I got 94.868 . with an angle of 18.435 degrees volts. All right, so which element do you guys want to determine the instantaneous power for first? The inductor. Camden said inductor first, so let's do that one. Okay. So the instantaneous power absorbed by an inductor only in terms of the voltage, because that's the only information that we know about it, is 1/2 times the magnitude of the voltage squared divided by omega L times the cosine of twice omega t plus twice theta v minus 90 degrees. So that's going to look like 1/2 times 94.868 volts squared. Omega L is just 3 kiloohms. Cosine, so twice omega is going to look like 4 times 10 to the 5. Radians per second. T is 10 microseconds. So that's 10 times 10 to the minus 6 seconds. I'm going to leave myself some space here. You'll see why in a moment. Plus twice theta v, so that's twice 18.435 degrees minus 90 degrees, close parentheses. Now let's talk about why I left that big gaping space there. So when I multiply my angular frequency twice omega times time, I wind up getting an angle that is expressed in radians, because radians per second times time measured in seconds is an angle in radians. Our phase angles have all been expressed in degrees. So we have a little bit of a problem here, in as much as our calculator can't interpret radians and degrees at the same time. I always choose to express my angular frequency effectively in degrees per second for this thing, just because my calculator 99% of the time is in degree mode already. So in order to facilitate that, I'm just going to include a simple conversion factor here, which is just going to be 180 degrees over pi. So that will make my resultant angle from multiplying omega t into an angle expressed in degrees. And so now I can put this into my calculator. Okay. So I'm going to do just that. I personally am going to break it up into 2 smaller parts, because this is a big, ugly thing to put in the calculator, and I don't want to make any mistakes. And for some of those Casios, they seem to run out of memory very quickly when doing long calculations. So I'm going to have 1/2 times the magnitude of what I have stored in my calculator as x squared divided by 3000. And I get that to be 3/2, which seems, so 1/2 times the magnitude of x squared. Yeah, I guess it's 3/2. So this whole first part right here comes out to be 3/2. And now I'm going to do the second part right here. So the cosine of 4 times 10 to the 5 times 10 times 10 to the minus 6 times 180 over pi plus twice the angle of what I have in my calculator is x minus 90. I get that bit looks like negative 0.9976, so 998 after rounding. Putting those two things together, negative 1.496 watts. So my answer was negative 1.495. Pretty darn close, maybe a little rounding error when I solved it the first time. Anybody have any questions about how we applied that one? So the resistor equation is going to be effectively the same basic setup, right? So let's look at the power for the current source, because that's where things are going to get marginally a little awkward, okay? I'm going to put a subscript R on this, oh, excuse me, L on this so that we know that it's for the inductor, okay? So for our current source, we have to use our generic equation because it's not a resistor or a capacitor or an inductor, right? So our generic equation is 1/2 Vm Im cosine theta V minus theta I plus 1/2 Vm Im cosine twice omega t plus theta V plus theta I. Now, let me scroll back up here to the top. We were asked to calculate the instantaneous power absorbed by each element. So what do we need to do to the current to give us absorbed power? Change the sign. So changing the sign on our phasor current is the same thing as adding or subtracting 180 degrees, okay? So this is going to look like 1/2 times our 94.868 volts times our current of 0.1 amps. Then I'm going to have the cosine of 18.435 minus 180 degrees. And again, just to be clear here, that 180-degree phase shift is just because we're calculating absorbed power for the source, not supplied power. If we were calculating supplied power, we could have left that phase angle at 0 degrees. To this, I'm going to wind up adding 1/2 VMIM, so that's 1/2 94.868 volts times 0.1 amps times the cosine of twice omega t, so that's going to look like 4 times 10 to the 5 radians per second, 10 times 10 to the minus 6 seconds. My conversion factor of 180 degrees over pi to put things in degrees, plus 18.435 degrees plus 180 degrees. Close parentheses. And once again, I'm going to break this up into two smaller parts so that my calculator doesn't have a panic attack. Okay. So 1/2 times 2 to the x times 0.1. I'm just going to store that as A. So this is going to look like 4.743 watts. Now I'm doing cosine of the 18.435 minus 180. Storing that in my calculator is B. So that looks like negative 0.949 after rounding. And I'm going to have that same 4.743 watts from 1/2 VMIM. And now I'm about to do that big ugly cosine 4 times 10 to the 5 stuff, right? So cosine 4 times 10 to the 5 times 10 times 10 to the minus 6 times 180 over pi plus 18.435. Angle of x plus 180. 0.381. That's going to look like what I have in my calculator is A times B plus A times C. And I got negative 2.694 watts. Just checking things out here. Exact same answer. I'll leave it to you guys to do the resistor calculation. Liam, did you have a question?
Yes.
Okay. All right. So this is probably the most annoying calculation that you've been asked to do in this class. That's why I took the time to really go through and break things down step by step. There are so many little places that you can accidentally make a mistake. So I wanted to clarify things here. So all we did to apply these equations was just take the constituent parts of our phasors that we needed and then plug those things directly in, right? Taking care to recognize that omega t by definition is going to be an angle expressed in radians. So we needed to include that conversion factor to put it in degrees so that we could just add our degree stuff together. If we chose to do everything in radians, we would need to just do the inverse of the conversion factor on the phase angle in degrees. Brandon, you had a question?
So for the DC portion, you subtract 180 degrees from the sine, so I'll make it 80.
So I said that the phase angle of my current was positive 180 degrees. If we look at our equation, we have theta v minus theta I for the DC part and theta v plus theta I for the AC part, right? So theta v minus positive 180 degrees, and then theta v plus positive 180 degrees. That being said, it wouldn't matter anyway, because 180 degrees and a negative 180 degrees are literally the exact same angle. But I was consistent with using positive 180 degrees for both things here. Okay, so what I'd like to do now, and really I'm just doing this because we're going to wind up using these relationships at the beginning of our next class meeting, is more formally looking at the math behind why 1/2 VMIM cosine theta v minus theta I comes out to be the average power, okay? So this is going to go back to some relationships that hopefully you guys learned probably in your pre-calculus classes, actually, or no, probably in Math 242 because it involves an integral. Okay. So let's call this average value of a periodic function. This will be fairly short and it's just a bunch of math, okay? So let's let x of t be a periodic function with period capital T. Now, to be clear here, x of t does not have to be sinusoidal by any stretch of the imagination. It just has to repeat at regular intervals. It just needs to be a periodic function. So we're going to work with things generically, and then we'll circle back around to how the sinusoids behave, okay? The average value of x, which I'm going to denote as capital X average, is going to be the integral over exactly one period of our periodic function x of t. And then we wind up multiplying that integral by a factor of 1 over t. So effectively what we're doing is we're just integrating over the interval and then dividing by the length of that integral to get the average value of our function. Hopefully you guys have seen this before, but if not, this should kind of make sense for what the process should be, okay? Realistically, you guys actually did this way back on homework assignment number 1 in this class. So now let's put things in context of our power relationship, right? So the average value of our instantaneous power should be 1 over t times the integral from 0 to t of our instantaneous power relationship. So let's use the generic relationship here. Sorry, I have omega there that I shouldn't. So theta v minus theta I plus 1/2 Vm Im cosine twice omega t plus theta v plus theta I, close my bracket, dt. So let's look at that second big ugly term first, right? So I'm integrating a sinusoidal function over one period. What should the result of that integration be? Let me draw a graph here. You're right. So we're just looking at the AC portion of this thing, okay? So I have something like this. So this looks to be one period. Exactly half of the time, our signal is above 0, and exactly half of the time, our signal is below 0. So when I integrate over one period, this whole thing goes to 0. Anytime we integrate a sinusoid over an integer number of periods, the result will always be 0. We're going to use this again on Friday after we get back from Mardi Gras. Blows my mind that I'm not going to see you guys for a week. Anyway. So all that we have left is this bit out here in front, which we've already established is just a constant. So literally all of it can be moved outside of the integral because not a single part of it is time dependent. So we wind up having 1 over capital T times 1/2 Vm Im cosine theta v minus theta I times the integral from 0 to t of dt. Well, it should be pretty darn obvious that this integral and this 1 over t just cancel each other out, leaving us with an average power of the exact representation that we were able to see just by looking at the graph and interpreting it well. All right, I'm done for today. For what it's worth, what we covered today is probably the easiest to understand, but the most difficult to calculate. What we're going to be talking about in our next class meeting after we cover effective values, which is just a tool to make the math easier, is complex power, which is significantly easier to calculate, but unfortunately much more difficult to actually understand what's going on. So I'm going to spend a lot of time trying to talk our way through what the different constituent components mean and relate them back to real world principles. Shelby, how may I help you? You do indeed get a formula sheet for exam 3. If somebody will send me an email, I will happily upload it for you guys if I haven't already done so, so that you can look at it. I do want to say this emphatically. I did not make it. I know that there are errors on it. I do not care because I do not think it's necessary. Realistically, the equation sheet for exam 3 is not needed. It is there for you guys to use as a reference, but I want you to understand, I know for a fact that there are errors on it. And because I fundamentally do not believe you need it, I will not waste my time fixing it.